In the previous lecture, we discussed the transport in ultra-small superconducting transaction systems and also looked the DC Josephson effect. In this lecture, we will discuss the AC Josephson effect in continuation to our discussion on the DC Josephson effect. Then there is another effect which is the inverse AC Josephson effect and superconducting quantum interference device, which is a manifestation of the macroscopic quantum mechanical tunneling phenomena. So the Josephson junction, what we discussed so far, consists of two superconducting regions interfaced with a thin insulating layer in the middle, and we solve the time-dependent Schrodinger equation for the system. For psi1 and psi2 are the wave functions for the Cooper pair or the condensate on either side. And after solving the equation by equating the real and imaginary parts, we got two sets of equations in the previous class, and there are actually two more equations, and that is what we are going to focus now. Okay, from the first two equations, which are on the time rate of change of the Cooper pair density, ρ1 and ρ2, ρ1 is on the psi1 side and ρ2 on the psi2 side, we got the first Josephson equation, which is the current density is a function of the phase difference of the wave functions between two sides. Okay, the first two equations after we solving the Schrodinger equation yielded the first Josephson equation. Okay, that is regarding the current density variation as a function of the phase difference. The next two equations in that are θ1 dot, which is k by h bar, ρ2 by ρ1 cos delta, delta is the phase difference, qv by 2h bar, where v is the applied voltage and q is the Cooper pair charge. And similarly for θ2, which is the rate of change of the phase on the psi2 side, where kappa by h bar, kappa is a coupling constant, ρ1 and ρ2 are the densities, delta is a phase difference, and plus qv by 2h bar. Okay, so the voltage is symmetrically applied between two sides. So half of the voltage on the right side, half of the voltage on the left side. So the rate of change of the phase difference, the delta dot, is θ2 dot minus θ1 dot, that is the difference of these two terms here, is going to give you qv by h bar, where v is the applied voltage. So what we are seeing here is the rate of change of the phase difference. That is what is going to decide the Josephson current here. Okay, is a function of the applied voltage. Okay, so the delta t, after we integrate this relation, is going to give you delta 0 plus q by h bar into v. We are assuming it's a function of t into integral dt. And this is actually the second Josephson equation. Okay, where delta 0 is the initial phase and Vt is the voltage applied. That can be a DC voltage which doesn't have any time dependence, then that V term will come out. Okay, and then integration is only over the time. So for a constant DC voltage, just like we mentioned now, the delta T is given by delta 0, this is the initial phase, q by h bar V0, that is the constant voltage applied, and the time. Okay, so the phase difference, that is delta, is a function of time when you have voltage applied. So, or it is, when you have constant voltage, it is going to linearly vary with time when you have with a constant voltage. Okay, so we can write this in terms of the Cooper pair charge, that is 2E, where Q is 2E, okay, 2E by h bar V0 into T, where V0 is the applied constant voltage, T is time. So what we are seeing here is delta is a linear function of time when you have voltage applied, but the current is a function of phase difference. So when you substitute this in the first Josephson equation, what we are seeing is the current is oscillatory because you have a delta term inside the sign, or it's an argument of the sign term, which is going to oscillate. The current is going to oscillate over time. Okay, that's what we are seeing. And if you look at the magnitude of this term, 2E by h bar into V, that is the frequency. This is of the form sine omega t, where omega is basically 2E by h bar into V, that is the omega term. Okay, this is the omega. Okay, and of course this represents a oscillating current. So when you apply DC voltage, what we have applied is a constant voltage or DC voltage across the junction, you get a AC current or an alternating current or an oscillating current through it. So when we did not apply any voltage, that is a DC Josephson effect, you got a DC current. Now when you apply an AC, so now when you apply a DC voltage, we get a AC current. Okay. Now if we consider the magnitude of this frequency, that is 2 E V by H. So basically 2E H bar. So H bar, if you take to we have H bar H by 2 pi. Okay. Now when you take 2 pi to the other side, what you can write is this is going to be 2EV by H, that is the frequency. Okay. Now this number is a very, very large number. Okay. What we are seeing is 483.6 into 10 to the power 12. Basically that is the, and volt is actually, that is, you have to multiply this, volt is 1 here. Okay, that many hertz, that's what it is. Or we are getting, if you apply 1 microvolt, that means you will get 483.6 megahertz. It's a very, very high frequency. Just 1 microvolt across the junction is going to give you 483 megahertz, or 10 microvolt is going to give you close to 5 gigahertz, right? Like 4.8 gigahertz, just 10 microvolt. So what happens is the radiation field, which is associated with the oscillating current, acts as an antenna, and it's actually going to emit this radiation. Okay, when you apply the voltage across the junction, the oscillating current given by this relation is going to act like an antenna and is going to emit radiation in this frequency. So what you got here is a very, very interesting situation where you can apply very small voltage across this junction and you can get a very high frequency. And not only that, it's a tunable It's a linearly tunable frequency source, okay, which actually can reach even terahertz range, okay. So in this paper, what they have done is they have generated terahertz using Josephson junction. Okay, the details are given in this reference. So you have basically Josephson junction with a bisco crystal, okay, and they are measuring the power in some arbitrary unit which is emitted by this, and as a function of the applied voltage. The details are given in this paper, okay. So what we are seeing is, as we vary the applied voltage, the peak is going to shift to various frequency regimes. So you can tune the emission frequency just by changing the voltage. That is what is being demonstrated in this paper, okay. There are many publications like this. This is one of them, okay. And similarly, in this paper, what they were doing is they had a Josephson junction which is trapped in a cavity, which is embedded in a microwave cavity. So this is like a lacing system for microwave. So you have a source. This Josephson junction can actually emit and absorb both, okay. So you have a kind of an artificial atom which actually can emit and absorb the radiation which is embedded in a cavity, and this is going to basically give you lacing action of microwave that is basically gated by the Josephson effect, okay. So this long conductor that you are seeing here in the center has to basically capacitance gap here on either side, okay. And you have a Josephson junction. Now this mirror, or this is actually a resonator, a superconducting microwave resonator which is tuned to this frequency, and this actually can capture the radiation emitted by the Josephson junction, and Josephson junction can capture this radiation back. So that is the lacing action there, okay. So that's what is represented here, okay. So this radiation, this cavity can act like a mirror and to provide lacing action for the microwave radiation emitted by the Josephson junctions, okay. So but there is a small catch here. The catch is the typical current should be like of the order of the IC or lower. IC is the critical current. So if you run a current which is above the critical current, there will not be any Josephson effect, because there will not be any superconductivity either, okay. So the maximum current is something of the order of a few microampere, so a few milliampere, okay. And the power delivered by this is actually in nanowatts, okay. So it's a very, very low power that you are going to get out of this single junction. So what you need is, you need multiple Josephson junction which actually emits coherently. Then only you get a continuous source of radiation coming out. Otherwise, they all will cancel each other. So there is an engineering part here where you need to have many Josephson junction. That's what is explained here also, okay. Many Josephson junctions emits this radiation coherently, okay. Then only this can actually work as a useful tunable high frequency radiation source, okay. That is the story with the AC Josephson effect. And now let us move on to another effect which is related to this AC Josephson effect, that is inverse AC Josephson effect, okay. So in this case, what we have is, we have a Josephson junction under the action of a DC plus AC voltage. You have V0, that is your DC term, and this is your AC term. But the condition here is the DC voltage far more or in magnitude compared to the magnitude or amplitude of the AC voltage. Okay. Now, from the Josephson equation, we have the delta T, the time varying phase difference is delta 0 divided plus Q by H bar integral Vt over dt. Now we have a voltage which is a function of time because you have an AC term. Okay. All right. Now, when you substitute this here, this is what we are going to get. Okay. Delta T. Now, we already have assumed that the AC part or the magnitude of the AC excitation is comparatively very small, and in that situation you can actually write this delta T as in the form sin x plus delta x, which is approximately equal to sin x plus delta x cos x. Okay. When you do this, the current that you are going to get will be of this form. This is this part, x part, and this part is your delta x part. Okay, delta x cos x part. Now we are interested in the DC current. Okay, that's what we are going to measure. Okay, and when you measure it, this is a time varying term. This first thing, so that is not going to give you any DC current. Okay, this is also a time varying term, not going to give you any DC current, but except for whenever this condition is met, omega equal Q by H bar into V0. Okay, or integral multiples of that. Okay, whenever you have this condition met, this term will be non-zero. Okay, so that means you have some kind of a resonant condition where when you applied DC voltage and the AC voltage, and AC frequency, applied DC voltage and the frequency of the AC voltage satisfy this relation, then you have a non-zero current flowing through it. Now, what you can write from this is V0, the DC voltage, that is basically across the junction, is NH bar Q by omega whenever there is a current through it. Okay, whenever there is a current flowing through it, there is the DC voltage given by this relation. This is the thing about N phi 0 by 2 pi, where phi 0 is the flux quantum. Phi 0 is the flux quantum. Okay. So there will be DC current flowing through the junction whenever this situation is satisfied. Okay. Or if you keep the frequency constant and vary the voltage, whenever this situation is satisfied, you will get a spike in the current. Okay. These spikes are actually called Shapiro spikes. Okay. Shapiro spikes. Shapiro spikes, which we will discuss when we discuss the quantum metrology in the next module. Okay. So you can, what this says is you can define the voltage very, very accurately if you define the omega. Okay. Or this phenomenon can be utilized for basically making universal voltage standard, and that is what is being done to standardize the voltage. It's called Josephson voltage standard, or in short JVS. JVS, that's what people call. Okay. So the assumption here is this is a fundamental constant, this is a fundamental constant, and n is also a constant. And the omega, the frequency, can be defined very accurately. Okay, because there are that is one assumption behind all the metrology, quantum metrology. So you can always define and apply the frequency very accurately. So then everything else here is defined to the best possible accuracy. So using this effect, you can define the voltage very, very accurately. That is the idea. Okay. So the device which is being used as a voltage standard consists of an array of this junction, which is shown here. Okay, and there is some kind of a microwave source which is going to be used as a AC source or radiation source. And what you would do is you will vary the voltage and measure the current. Whenever this is satisfied, you will get a step in the current. Okay, that is the idea. Okay, so this is a this is the schematic, and this is a picture of an actual device which is configured in a very similar way, where you have an array of Josephson junctions, which can consist of thousands of Josephson junctions. Okay, so depending upon how many, what is the voltage that you want to standardize, the number of junction also will go up accordingly. Okay, because every Josephson junction is going to give you only V0. Then if you need more, you have to put them in series. Okay. So a 10 millivolt voltage standard, Josephson voltage standard, and a 1 volt voltage standard will be different in size. They will have more junctions. Okay. Anyway, that is the technology aspect. But the point here is this phenomenon, Josephson inverse AC Josephson effect, is the main workhorse behind the Josephson voltage standard. It's one of the quantum metrology standards. Okay. Now, let us discuss one more effect, which is related to Josephson effect, that is called macroscopic quantum interference, or basically it's a SQUID. Okay, superconducting quantum interference device. Okay, SQUID. So what we have is a superconducting quantum interference device. In short, it is also called SQUID. SQUID. So we got here two Josephson junctions in parallel. So there is one here and the second here, two Josephson junctions parallel, which are, the whole configuration is, it's like an Aharonov ring, but you got one Josephson junction each of the ring. Okay. So you have one superconductor here on the source side, you have another superconductor here which is on the drain side, and they are merged through two Josephson junctions A and B. Okay. Now, we know this is an Aharonov ring configuration, so we have also a magnetic field which is running normal to the plane, perpendicular to this plane. Okay. The phase difference for the charge carriers propagating through upper arm with the lower arm basically has two parts. Okay, one, the natural phase that is going to get accumulated, the difference of the natural phase is going to accumulate by this length, and that let's assume that that is same because this is a symmetric ring and both are delta zero. Now you also have a phase that we learned from the Aharonov effect, that is an AB phase that depends on the magnetic field. Okay, and that is of this form, 2E by h bar A dot ds. Okay, that is for the full travel around the ring. Okay, and A dot ds is the phi, that is a field enclosed in this ring. But now the charge carriers take only half the path, so the phase accumulated will be E by h bar into phi, where 2E by h bar into phi is the actual. A dot ds, when you take it, you will get phi. Okay, so E by h bar into phi. Phi is the field. Okay, magnetic flux. Now for the lower arm, there will be sign change because the direction of propagation and the field are, and the vector potential are in opposite direction. So there will be a minus sign or negative sign there. Okay, for the lower arm. So now the phase difference of the phase difference that between the charge carriers propagating through the lower and upper arm will be basically delta A minus delta B, that is basically 2E by h bar into phi, where phi is the overall flux which is going through the ring. Okay, and the current basically is a function of this phase difference. Okay, because you have two paths, they can interfere at this point, and the overall current will be sum of these two. And you can simplify this, and what you are going to get is a formula which looks like this, where I0 sine delta 0 cos E by h bar into phi. And if you look at this formula is basically very similar to a Young's double slit interference formula, where you have a fastly oscillating term E by h bar. This is a very small term. Okay, now you also have a slowly varying term delta 0. Okay, if you plot this, you are going to get a profile which looks something like this, where you have the profile and you have very really fast oscillation, and the frequency of the fast oscillation is given by E by h bar by E. Okay, so the periodicity of this fast oscillation is given by h by 2e. Okay, h by 2e is basically the magnetic flux quantum phi 0. That means whenever the field through this ring changes by phi 0, that is h by 2e, you will get a full oscillation of the current. Okay, and this phi 0, if you look at the actual numbers, phi 0 is a very very small quantity, that is approximately 2 into 10 to the power minus 15 Weber, or in terms of Gauss centimeter square, that is 2 into 10 to the power minus 7 Gauss centimeter square. It's a very very small number. So you have a device now whose current undergoes a full oscillation, shows high nonlinearity when the field through that ring is changed by like 2 to the power minus 15 Weber or 10 to the power minus 7 Gauss centimeter square. Okay, so this is an interesting aspect where one can use this to detect a change in very small field. If the field changes by this much, you get a full change in the you get complete oscillation of the current. So this is what is used for. This is the principle of the discrete magnetometer, where you have a loop and you are measuring the current through a loop as a function of the field, or whenever the field varies through that, you get to change the current, by which you can calibrate the device to detect really small field. Okay, that also we will discuss when we discuss the quantum metrology part. Okay, now we have summarized the application, the principles and applications of all the Josephson effect in the last two lectures. Okay.